I will explain in this talk what this is, superstatistics, what people mean by it, and talk about typical universality classes of this approach. And then I come to applications. My first two applications are really in turbulence, Lagrangian fully developed turbulence, and quantum turbulence, actually. And in the second part, I will come to applications really for planet Earth and things like that. So we'll talk about atmospheric turbulence, wind gusts, and sea level fluctuations, and try to convince you that the concept is a useful one in this area. Now, what is superstatistics? A lot of complex systems, whatever they are in environment or planet Earth or whatever you're thinking of, are often described by a mixture of different statistics on different time scales. And so the very simplest example is really just think of a Brownian particle described, let's say, by the Ornstein-Uhlenbeck process, and then assume this particle moves through a changing environment. So for a while it sees temperature beta 1, inverse temperature beta 1, then after a while it moves to a different position where it's a different temperature beta 2, or inverse temperature beta 2. And so in this very simple example, you have a mixture of two statistics. One is just ordinary local Brownian motion with a given inverse temperature, but superimposed to that is the stochastic process of inverse temperatures beta I at the various spatial locations. So one can, of course, construct a dynamical realization of this idea. So this is done here. You take just a linear Langevin equation, but you can, of course, do more complicated things as well. But just for illustration, take a linear damping term minus gamma v, where v is the velocity of this Brownian particle, and you add Gaussian white noise denoted by L of t here, which is just the derivative of the Wiener process. And then the new thing is you simply regard these parameters gamma and sigma, which you usually keep constant in your stochastic differential equation. You regard those as a fluctuating stochastic process as well, where these changes of gamma and sigma are on a much larger time scale than the local relaxation time of the system. So just to be concrete, let me take a concrete example. We take beta, which from non-equilibrium statistical mechanics, we know the inverse temperature beta is gamma over 2 sigma squared, and we just let that beta then fluctuate with a probability distribution, which I choose in this simple example to be the chi-square distribution, right? So this is this f of beta up there. Well, and then that is a very generic probability distribution. You get it when you have n Gaussian random variables and square them. And then clearly the conditional probability of this Brownian particle given a particular temperature beta is still the Gaussian distribution, e to the minus half beta v squared. The joint probability is then simply the product f of beta times p of v given the beta. But what experimentalists then often measure is the marginal probability density, which you obtain by integrating over all these inverse temperatures beta. And if you plug in these formulas, then you end up with this formula. So you see the P of V, the stationary distribution of this system where the parameters fluctuate, is not anymore a Gaussian distribution, but it's a power law that you get here simply from this integration over the fluctuating beta. And so you may regard, if you like, that as a kind of generalized Boltzmann factor, which is generalized in the sense that due to fluctuations we now have a power law rather than exponential decay, right? And the relation to the power law exponent, which is denoted by Q here, is simply it's 1 plus 2 over n plus 1, where n is the number of degrees of freedom that enter into this chi-square distribution. Now, this is just one example, but the idea can be generalized very much. And so, for example, beta need not to be the inverse temperature as in this example, but it could be any parameter in your system in which you're interested in. And another thing is, of course, you could also look at general probabilities, f of beta of this spatial distribution of the temperature. You don't have to take the chi-square distribution. That was just an example. And finally, the third generalization is you don't need to take a linear Langevin equation. You could do your favorite statistical mechanics system, take that Hamiltonian of that system, and then regard the temperature of your favorite statistical mechanics system as an additional random variable. Now, there's clearly then a superposition of two statistics, that of beta and that of ordinary statistical mechanics, and just for that reason that was called superstatistics in a paper by Eddie Cohn and myself 10 years ago. It's just a name, so it's an abbreviation of the superposition. It's not meant to be superior to anything else. People have extended this concept and applied it to various systems in biology and finance and networks and so on. And what you really need for this approach, that it works properly, is a proper timescale separation, right? So the Brownian particle, to come back to this very first example, needs to have enough time to relax to the local equilibrium, which is the Gaussian distribution, before the next change of the macroscopic temperature takes place. Then this approach works pretty well. And if you like, then you can think of these integrated Boltzmann factors integrated with the inverse temperature distribution in the various spatial cells. You can think of those as generalized Boltzmann factors. Now, here's a little bit what people did on the theoretical aspects of that. You can do variational principles for that. You can do fluctuation theorems for that. You can define more general entropies that effectively reproduce that. You can look at applications in random matrix theory. You can do it for networks. You can do it for path integrals. You know, the path integral in quantum mechanics is basically a Brownian motion process. And if you let then this diffusion constant also fluctuate, then the path integral becomes superstatistical in this sense. On the more practical side, where it turns out to be really useful, people applied it very much to turbulence. So I'll come to these turbulence applications in a minute. And also it has been applied to a variety of other systems, like high energy scattering processes in particle physics, where if you are at CERN at a collider experiment, then they look at little particles in a very small volume, and therefore the temperature there is also not constant and things like that. And what I want to propose here in this talk, that there's plenty of scope to apply these types of techniques to atmospheric and climate science as well. Now, before I come to these applications, let me just mention three main classes of superstatistics, which turn out to come up again and again in the experimental data that we try to analyze in this way. One is chi-square superstatistics, so that was basically this example I mentioned in the very beginning, that the f of beta is the chi-square or gamma distribution. And the other thing is that very often you find inverse chi-square superstatistics where the temperature or inverse temperature distribution is given by a so-called inverse chi-square distribution. And another very important class of systems is those described by log normal superstatistics. So why do we have these three main classes that can be understood pretty straightforwardly? Let's say we have a complex system. It may be your climate system or atmospheric system or whatever you have in mind, and there are then usually many microscopic random variables xi j, and of course we have then the ordinary central limit theorem. If the xi j are independent or nearly independent, that means the underlying chaotic dynamic system must be very strongly mixing, then a rescaled sum of these xi j's converges to a Gaussian random variable regarding the initial values as a random variable. And now your complex system may have several of these Gaussian random variables, right? So these are denoted by x1 up to xn. And now remember that in the original concept, which we introduced with Eddie Cohn, the beta was really in inverse temperature. So inverse temperature is always positive, right? Or nearly always positive. And therefore, if you regard now this inverse temperature as being produced by these various degrees of freedom in your system, then very often you have simply this form that you add up the Gaussian random variables in your systems, but square them because beta is positive, right? So therefore, from this empirical argument, you get that the f of beta, which is the chi-square distribution here, is very generic in a sense in the system. It's the simplest way to produce something positive out of n Gaussian random variables if these are added. So that would be this chi-square superstatistics, but the inverse chi-square superstatistics, well, rather than regarding beta to be a sum of these Gaussian random variables squared, you may regard the inverse temperature to be directly composed of these random variables, and then by simple transformation of random variables you end up with this distribution f of beta there, which is called the inverse chi-square distribution, and that has now the 1 over beta in the exponential there rather than beta in the exponential. And the interesting thing is, if you assume this type of superstatistics, then the generalized Boltzmann factors, which are obtained by taking the ordinary Boltzmann factor e to the minus beta e, integrating with this f of beta over all beta, then they decay as e to the minus a constant times the square root of the energy. So you have, if for example, if you think of kinetic energy, then kinetic energy is basically velocity squared. The square root out of that gives then exponential tails in the velocity rather than the velocity squared. That is typical for this type of system. And then the third class that is important, well, that is really related to turbulence and stuff like that, because we know in turbulence we have a cascade-like random process. Energy comes from big scales and dissipates down to smaller scales, and very often this process is described by a multiplicative process. So the random variables xi j that I mentioned before are now product random variables, and the random variables x1 are very often in these types of systems products of the xi j, and then by taking the logarithm of that product you get that the logarithm of x1 then becomes a Gaussian random variable due to if the xi j's are nearly independent. And then if you transform back to the original beta, it simply means that the beta is then log normally distributed. And this last class is really very much in the spirit of the so-called K62 theory in turbulence, where the energy dissipation is log normally distributed. Just in turbulence, the beta may have different meanings. It may not be the physical temperature of the flow, but it is related to energy dissipation. So these are the three main classes we are interested in, and now I want to illustrate you this general stuff by concrete examples and also show you that the concept is useful. So our first example is Lagrangian fully developed turbulence. So in Lagrangian turbulence, you follow a particular test particle in the turbulent flow, rather than trying to understand the entire spatiotemporal pattern of your turbulent flow, which is terribly complicated. You try just to follow one particle in the flow and produce a good model for that, how it's behaving, right? So this is an actual measurement of Eberhard Bodenschatz at the time still at Cornell University, and it shows the acceleration of a single particle in the flow. The color coding denotes the acceleration that this particle sees in the turbulent flow. And blue, green, yellow is the color scheme. You see these tiny test particles see incredibly high accelerations, which have been directly measured in these turbulent flows. The reason is simply that they are really tiny, have a small mass, so a small mass corresponds to a huge acceleration if the forces are of order 1. So these measurements have been done for the acceleration of the test particles, and then naturally you do probability densities of these accelerations in the turbulent flow, and that is what Bodenschatz and others got. Experimentally, you see up there on the vertical axis you have the logarithm of the acceleration. No, on the vertical axis you have the probability to see a particular acceleration A, and on the horizontal axis it's the acceleration in units of the standard deviation. And the histogram that you see that has been measured is highly non-Gaussian, very strongly non-Gaussian, and there are also some strange correlation patterns which are measured, which is this color diagram there. So you have to the right, you have AX, the acceleration of this test particle in X direction, and this is AY, the acceleration in Y direction. And these two components are correlated, and the correlation function has this strange pattern there. Now, these are things we want to understand, and there are two possible approaches. Very often people say, oh, turbulence is simply too complicated to do the statistical mechanics or so, or it's too non-equilibrium. Then people say, oh, it's so we simply give up, it's too complicated, it's the old turbulence problem. Or the other approach is you simply make a simple model of it, right? And the model I want to show you is indeed a superstatistical solvable model for these types of Lagrangian turbulence measurements. And here we go. So the idea is the following. You start from something very simple, a linear stochastic differential equation again, right? So we regard u of t to be the velocity difference of this Lagrangian test particle on a small timescale tau, and if the timescale tau goes to 0, then you get from that the acceleration of this test particle. And now the idea is that locally, in fact, in this turbulent flow, the dynamics for the single particle, not for all of them, just for the single particle, is pretty simple. You have a relaxation term, so u dot is minus gamma u, and then there's some rotational element in the flow, so the particle rotates due to the eddies in the flow, right? So that is the second term in this equation. And then the deterministic chaos in the Navier-Stokes equation is simply evolving very fast, and therefore you approximate that chaos by Gaussian white noise L of t. And so gamma and b are a priori constants, and that model would miserably fail to reproduce Bodenschatz measurements because it produces a Gaussian stochastic process. But the idea is that in the turbulent flow now the parameters gamma and b, and also the direction of the n, this normalized vector producing rotation, they simply fluctuate in a superstatistical way. So you make these parameters random variables as well. And that makes absolutely sense, because we know if a particle moves through the turbulent flow, then for a while it sees a very strong dissipation, and for some other time it sees much less dissipation. So there are fluctuations of the environment of this test particle. So we simply make this a superstatistical differential equation, and then you can calculate a little bit, relate the parameters to standard language of the turbulence people, like Reynolds numbers and so on, and out comes then that it's an additional assumption. You assume that the parameter beta, which in this case is related to the energy dissipation rather than the temperature of the flow, is log normally distributed in the spirit of the Kolmogorov 62 theory. And then you get this from this model, then you get the following prediction for the acceleration. It's simply the Boltzmann factor, if you like, the e to the minus ax squared. The meaning of the symbols in the turbulent flow is different. It's now the acceleration or the velocity difference rather than the velocity. And you let the variance fluctuate with this log normal distribution, and you integrate over all betas because that is what your measurements do. You do a long-term measurement of the acceleration, and out comes this formula up there, and that fits the data perfectly of the Bodensatz. Here is the solid line that is just the prediction of this superstatistical model. And also other things like these correlations between the components can be understood, and you can calculate it. This is what comes out of the model. Here's AX versus AY, and the logarithm of the ratio of the joint probability over the product of the single probabilities to observe accelerations AX and AY. That is the prediction of the model, and it is just the same as what is Bodensatz is measuring in his paper there. So that means it works, but there's a big mystery here, and I really want to emphasize that we start from a very nonlinear, very complicated equation, the Navier-Stokes equation, and the question is, why does this highly nonlinear equation generate such a simple, effective superstatistical process? And it's only simple if you follow a single particle. It's not simple. It's terribly complicated if you try to understand the entire pattern that the turbulence generates in space and time. But why does it simplify for a single particle in that way? That's a big question. I don't know the answer. Now, before I come to the environmental applications, let me do a brief encounter with quantum turbulence. People recently became interested in fully developed turbulence of quantum liquids. So if you have, for example, liquid helium, you cool it down to very low temperatures, then this thing still obeys or can exhibit turbulent behavior if you drive it very strongly. But it's a different type of turbulence, because from quantum mechanics then you get additional constraints on the vorticities as circulation is quantized, and it in fact is a very interesting quantum mechanical problem. You have a network of complicated one-dimensional vortex lines that merge and that can dissolve again. So it's a nice system, and in the very beginning of the research, I would say, because theoreticians even can't agree on the equations that describe quantum turbulence, right? So again, they start from a nonlinear Schrödinger equations, but others say you have to do something else. Anyway, experimentalists took up this problem. They looked at the turbulence of these quantum liquids and measured the probability density of the velocity, again, of a single tracer particle in this quantum liquid. And that is the result. Here's the velocity. Now it's not the velocity difference, it's the velocity really, and this is the probability density to find a particular velocity component of the particle. And that is the result, these red and blue data points. So it's strongly non-Gaussian, this velocity distribution. So again, a simple Gaussian model would fail, and in fact, it is a power law. And now you can apply, again, the superstatistical formalism. You say, oh, again, there's a relaxation constant, some rotation. You calculate through this model. You think about plausible distributions of the fluctuating parameter, which is different in quantum turbulence, because what is really relevant is the mean distance to the nearest vortex line in your system. And out comes a prediction. This is really a prediction for the probability density of the velocity, which is a power law distribution. And so we published that in this rapid communication, and it works well. It really gives the essential features of these measurements, right? So here you have another example of superstatistics, but in this case, it's the chi-square superstatistics. So that's important to note. For the ordinary turbulence, it was velocity difference and log normal superstatistics. Here it's chi-square superstatistics. Now, let me come to environmental time series. And again, we have a similar problem as in quantum turbulence. Very often, the people don't even agree on the equations that describe all this. Yes, the question?
I was curious, do people have some agreement on what the cascade should look like?
The cascade is also very intensively discussed. So in quantum turbulence, you do have a cascade, and people in Newcastle claim even there's also an inverse cascade, which is more important in quantum turbulence. So also energy going from the smaller scales to higher scales. So the cascade picture is very delicate there. Okay. Anyway, let's look at these environmental systems. Again, we don't really know what the equations are sometimes. We treat these systems as a black box, let's say, and now what can we do? The problem there is that you basically have a time series of your environmental data, whatever they are, and you want now to construct a suitable superstatistical model for that. And I employ now a method which we published with Eddie Cohn and Harry Sweeney in 2005. So, in fact, Eddie got the Boltzmann medal after that in 2005, I think, and Harry Sweeney got it in 2013, so I'm in good company there in this paper. So, what we did is we said we want to simply extract the most important superstatistic parameters from a given time series. How do we do that? The assumption is that locally, again, the process is simple. Let's say a simple Gaussian stochastic process. So if you do a time slicing of your time series, then in a certain window size, there should be more or less Gaussian behavior. Now, how do you find this Gaussian behavior? You look at the kurtosis, because kurtosis is free for a Gaussian distribution, and now you vary your window size where you the slicing of your time series in such a way that you get a kurtosis 3 if you average over the entire time series. So that gives you kind of an optimum window size, and then you can do a few additional statistical tests that tell you how good this approximation is, and define a parameter epsilon that measures how well this superstatistical approximation is. This is a little bit in the sense of the talk we heard yesterday of a person from Sudley who looked at maxima within these windows. We just look at the Gaussian statistics there, and then okay, so then you can extract from the time series with this algorithm the relevant parameters like the beta, the effective beta parameter in the given time slice, and then with this algorithm you can then test the algorithm with surrogate data and things like that. Anyway, it gives you an algorithm, given a time series, it produces you the f of beta out of it. And that is the result here for wind velocities. So this is really now wind. You have wind gusts. These are measured often at airports or wherever. And the velocity difference on a given time scale delta, that is of interest here for this wind. And now you see here for these data which we analyzed, clearly the green line fits the data best, and the green line in this case is inverse chi-square superstatistics. So it's an inverse chi-square distribution that the algorithm gives for these wind data. So that means we have the third of the three universality classes here, inverse superstatistics for wind data. And now this is the original histogram of these wind gusts. Again, you see they are kind of near exponential tails, which you can explain with these types of models. And of course, the tail behavior of all these things are very important for extreme event statistics, because you want to do generalized extreme value statistics, and there it depends very much what these tails do. So it's very important to get that right, what type of superstatistics your data are doing. Here's I mentioned in the very beginning that the time scale ratio of the local relaxation time to the time scale where the beta parameter fluctuates must be big, okay? And therefore, this gives you here this time scale ratio as a function of the delta, the separation on which we look at the wind velocity differences, and it is indeed of the order of 30. So the algorithm shows then that is self-consistent. This ratio is big. Another interesting thing is if you have turbulent problems or other data that evolve seemingly more or less randomly, very often you have a skewness in the data, which is not that easy to model. And also there we have some tricks how to do that, but I skip these details. You can read it up in some of the papers. Now, the last thing I want to talk about is sea level fluctuations, because very recently PSRC, which is our main funding organization here in the UK, funded a big grant connecting 10 universities. One of them is Queen Mary, where I am. And so they have the idea, well, they want to understand the statistics of flooding events. And flooding is really extreme event statistics for rainfall, for sea level, for whatever you're interested in, right? So they, so in this grant which just started, we look in particular onto the statistics of sea levels, and Paula Basser, who's here, is working on that. And for these sea levels, you have again a deterministic part which is quasi-periodic and is called astronomical tide. And then there's some fluctuating part, and our goal is to better understand this fluctuating part. And it turns out now that for these data, which is very recent work, they seem to be somewhat between log normal superstatistics and chi-square superstatistics. So let me show you that. Again, we are very much interested in these details, because ultimately for this grant we want to do extreme value distributions and estimate very precisely for the British government what the probability of clustered recurrence of flooding events is, right? So we looked at that, and here you see typical pictures for sea levels here in the UK. So in the top picture you see the time in days, and that is the sea level in meters. So it fluctuates with 2, 3, 4 meters or so, which is just the tide. And you see these astronomical tide is produced by the moon and the sun and all that, which these people deal in a quasi-periodic way, if you like, if you're a mathematician. And then added to that is a fluctuating part, which is this part, and that is what we are trying to understand in our models. And so here's again how this fluctuating part fits. It's a log normal fit up there, it's a chi-square fit there, and it's an inverse chi-square distribution fit there. And you see it's somewhere between log normal and chi-square superstatistics. I skipped the surface temperature things we did, but that's another interesting thing. Here's the summary. Superstatistical techniques can be generally applied to complex systems if there's timescales separate. It's sort of a simple method to make methods from statistical mechanics work by simply making the parameters fluctuate in addition, right? And there are 3 major universality classes, and I gave you 3 examples of all of them. So the fully developed 3D turbulence seems to be well described by log normal superstatistics, the quantum turbulence by chi-square superstatistics, and the atmospheric turbulence by inverse chi-square superstatistics. And I think I finished here.
Thank you very much. Well, there is time for two, let's say, couple of short questions.
I think there's two issues here with the turbulence. One is the universality issue, and I mean you're sticking with log normality, but of course it goes to log Levy, not just log normality. And but there was a debate about this in the 80s because there's also the small scale limit. And so Mandelbrot, in fact, even said, there's no universality classes for these cascade processes because there's a singular small scale limit you have to deal with. But at the end of the day, the conclusion of debates in the 90s and whatnot is that you have effectively universality classes, but they correspond to Levy, not just log, not just Gaussian. But you have these power law tails that arise because of the singular small scale cascade limit. And so there's been quite a lot of results in the atmosphere and also in laboratory turbulence about power law tails on velocity fluctuations, temperature fluctuations, and all kinds of stuff. So anyway, I think your framework is too restricted in as much as it's log normal, and also it doesn't take into account the small scale limit problem. I mean, Landau, even in the 60s, said you have the problem if you really did have log normal statistics, say in the velocity field, as soon as you went to larger scales and you started averaging, then you no longer have log normals.
Yeah.
So the solution to that is that you get power laws, in fact.
No, I wouldn't say it's restricted. It's more the opposite. A priori, this formalism allows for any distribution of f of beta, right? Now, for the data that we have got from Ebert-Bodenschatz, I must admit we tried various fits, and for these data, simply the log normal distribution, which is in the spirit of Kolmogorov's original ideas, gives the best fit of the data. But that does not say that in other experiments you have other distributions, and that in fact I would agree with you that probably all these things are less universal than people think. It depends sometimes very much on the details of the system, on the small scale, on the boundary conditions, which type of velocity distributions you get. And I would actually think while one should be more pragmatic and say, for a given experimental situation, what is the best fit of the data? Now, the Bodenschatz measurements are something very new as compared to the work in the 80s and 90s that you measured, because for the first time in 2001 he measured really the Lagrangian turbulence statistics rather than the Eulerian. The statistics you refer to refers to the entire lab frame where you try to understand the spatiotemporal chaos of turbulence in the lab frame. But he goes into the Lagrangian frame, so he follows a single particle. And for that type of turbulence, people again define, say, scaling exponents and things like that. They're different from the Eulerian scaling exponents. So I don't think it is too restricted. Log normal is one possible example, but it's in fact the point of my talk is that you may have other turbulent systems where other distributions are relevant, and quantum turbulence is one example. If you want to make a full theory of quantum theory, I would think one would have to make a Kolmogorov-like theory where the log normal is replaced by the chi-square, actually.
Well, yeah, but the universality just says you have this Levy index.
I would like to know just another question. So please, then please discuss privately. So because we are a little behind our schedule.
Right, on these random distributions that you put in that are crucial for your theory, is there actually any way to measure them directly? I mean, with local temperature fluctuations or fluctuations of respective variables? Because you have mentioned a lot of experiments.
That's right, yeah. I mean, that would be really fantastic. So for the Lagrangian turbulence, in particular the quantum turbulence, it would be fantastic if one could measure directly this fluctuating parameter. But that is very hard to do. But you're right, with this one could really test the theory. One could then look at joint probability distributions, let's say, of the velocity and this parameter, if one could do these measurements. But it hasn't been done, so all what people so far managed to do is always looking at the marginal distributions of a certain observable light velocity, and then everything is averaged in the long term here.
So also for none of the other experiments, not necessarily turbulence, but we mentioned a lot of applications that has never been done.
Well,
Other experiments for any.
well, I could imagine for the environmental things which are just in the beginning right now, that one could do their more detailed measurements. For the turbulence, I'm not so optimistic.
Okay, I think we thank again the speaker.